Right, so we're going to be getting into more kinds of linear relationships and getting into equations a lot more now. Direct variation, and this is a specific topic we're going to cover within direct variation, is a type of a linear relationship. And to illustrate it, we're going to go with an example first. A recipe for paella calls for a cup of rice to make 5 servings. So if we make the table here, every cup of rice, and we'll just go 1, 2, 3, 4, 5. Every cup is going to make 5 servings. So if we had 1 cup, 5 servings, 2 cups, 10 servings, 3 cups, 15, 20, and 25. Definitely a linear pattern. But this specific one, we're going to start writing equations for. We want to relate y to the value of x. So when we look at this, every single time, how did we calculate going from the number of cups of rice to the number of servings? Every single time we took the value of x and we multiplied it by 5. So the equation is y equals 5 times x. If x is cups of rice and y is servings. So the independent and dependent variable. So this represents a direct variation, and what a direct variation is, it's a special linear relationship. You want to make sure you get this down, this general form. Oops, I don't know why that extra mark went in there, but this general form of a direct variation is y equals kx. So the direct variation can be written in this form. K represents what we call, is non-zero, but it represents what we call the constant of variation. So with our previous one, y equals 5x, the equation is a is a direct variation, and the constant of variation is 5. It's basically the number that tells you how x is related to y. So we're going to do some identifying, but I'm going to start with identifying for you which ones are direct variation. So you may have to do a little bit of extra manipulation to tell whether an equation represents a direct variation. But what's the big characteristic here? We're trying to get y alone. So in this first one, if we divide by 4 on both sides, we get negative 3/4 x equals y. So is that a direct variation? Check. Yes, it is. And the constant variation k is negative 3/4, because that's how x is related to y, by using the number negative 3/4. It's negative 3/4 of x is y. If we look at this next equation, subtract 4x to get y alone, we get y equals negative 4x plus 3. So this equation does not fit into the direct variation model because kx, there's no value on the end here. There's no plus anything on the end. So if there's a constant term included, that's not a direct variation. So we can't identify the constant of variation either. Because x isn't just related to y by the number in front of x, it also is factored in that adding on 3. For the last one here, get y alone by adding 5x. Y equals 5x, and we already identified an equation like this. Yes, it is, and k equals 5. So keep that in mind, because we're going to kind of combine these ideas together in a minute here. So characteristics of direct variation, besides their equations, there's also characteristics within their tables and within their graphs that we need to be aware of. So you want to make sure you're recording this information. But if we have this table, this actually does represent a direct variation. If you look at the relationship between x and y, 2 to 6, 4 to 12, 6 to 18, y equals, we need to figure out what our constant of variation is. So our constant of variation is what do we multiply x by to get y every time, and this one should be fairly obvious. Y equals 3x. So if there's a direct, you almost think of it as direct number that if I multiply x by to get to y, that represents a direct variation, as long as it's consistent in every pairing there. So what you'll notice then is, I have these notes here for us. If we take the y value over the x value, 12 over 4, 6 over 2, 18 over 6. Notice every time I divide the y value in the coordinate by the x value in the coordinate, I end up with the same value. I end up with the same value, which is the constant variation. So y over x is the constant of variation. Constant of variation. Now, if we look at the graph of this, and I'm going to go ahead and bring up some scaling here. Right, if I put these points on here now that I have a scale, 2, 6, 4, 12, 6, 18, and I extend this graph-wise, what are we going to notice about a direct variation? Well, two characteristics are really important. One, it's linear, and two, the other characteristic is take a look at the intercepts. X-intercept, Y-intercept, whichever way you want to think of it, but we're really going to focus in general most of the time on the Y-intercept, and so we're going to say the Y-intercept or the intercept in general here is 0, 0. So visually, a direct variation is going to go through the point, is always going to go through the origin, linear and 0, 0. So these factors all together kind of give you direct variation. So here's the you-do, kind of combining the things we just talked about, which show a direct variation. Go ahead and pause the video and think about it. But if we look at this, we're always trying to get y alone. I'm going to start with the equations. Y equals 4x plus 7. Not a direct variation because of the 7. So I'm just going to put an x here to say, nope, not a direct variation. Get y alone here. Divide by negative 3. Negative 2x equals y. Yes, it is a direct variation because it's written in the form y equals kx. K in this case equals negative 2. Okay, going on to the graph here at the bottom of left. The characteristics that make a direct variation has to be linear, and it has to go through 0, 0. So check and check. Both of those characteristics work, so this is a direct variation. To find the k value, we want to look at, okay, here's a point, 1, 4. What's the relationship between the x and y value? It's a factor of 4. What you might also notice, let's do our rise and our run here, 4 and 1. That k value, also the slope of the line. Okay, from the table, how do we tell if these are direct variations? Well, we need to look at the points, and we need to see if it's a direct variation, all the y's over the x's should equal. So does negative 2 over 1 equal 0 over 3 equal 4 over 7? No, actually none of those are even equal. So this is not a direct variation. If we look at the y's over x's in our second table here, negative 10 over 2.5 is negative 4. Negative 20 over 5 is negative 4. Negative 30 over 7.5 is also negative 4. So this represents a direct variation where k is equal to negative 4. So we want to be able to recognize the direct variation, but we also want to be able to work with more kind of real life and connecting this a little bit to our roller coasters and science. Distance, time, and rate, or the other word is we use for that is speed, is definitely related to direct variation. And if we think about this situation, a group of people tubing down a river at an average speed of 2 miles per hour. So if we consider, I don't know why my pen keeps doing that. If we consider 0, 1, 2, 3, and 4 hours, thinking about what the speed means. If they're going 2 miles per hour and they float for 1 hour, they're going to go 2 miles. If they float for 2 hours, they're going to go 4 miles. If they float for 3 hours, it's going to be 6. 4 is going to be 8. So remember, miles per hour, you're thinking how many miles can they go in 1 hour? 2 miles in 1 hour is what that miles per hour actually means. So if we're looking at this and we want to take this situation and write an equation and graph it, what we'll notice is it relates to a direct variation. So we have our table. Our equation is how do we go from the x values to the y values. So in this case, I'm writing y equals 2x, but if you notice, I'm trying to use these different letters here, and we'll see why in a second. I'm just going to go ahead and replace those. So instead of y, we have d. Instead of x, we have t. So d equals 2 times t. We graph these points, 0, 0, 1, 2, 2, 4, 3, 6. This is the hours, and this is the miles that you go. So what can we notice about this line when it comes to giving these specific values, hours and miles? Well, the slope of this line is 2. The constant of variation is also 2. But what does that 2 actually represent? It actually represents the 2 here, the 2 here, represents the speed or the rate. So when it comes to speed and rate and distance and time, this actually is always a direct variation relationship. So if we think about the equation we just wrote, d equals 2 times t, distance equals 2 times time, we could actually use this equation to help us write a more general form, where the distance is equal to, instead of, and I'm going to go ahead and define these, d equals distance, instead of that actual number of how fast they were going, we're going to substitute it out here with the word rate, the variable r to stand for the rate. So how fast are they going? So we're going to relate this to our roller coasters because we're going to be finding the rate that your marble car is actually moving through the roller coaster. How are we going to do that? Well, we're going to measure the distance your marble's traveling and the time. So last thing here is a you-do on distance, rate, and time. And so you're going to use this table below to find the rate of speed traveled. A couple of ways to do it, but we want to kind of do this complete view of direct variation here. So if we're looking at our t's and our d's, here are our x's and our y's, how do we relate those? Well, the distance traveled is equal to, and for all of these, it's 8 times the time. So if we graph this, and I'm going to go 8, 16, 24, 32. If we graph this, 0, 0, 1, 8, 2, 16, 3, 24, 4, 32. What I really want you to see, and I'm not putting an arrow on the other end because we don't really want to go negative. We don't really want to go negative values for hours and distance. What I really want you to notice, though, look at this slope. Up 8 over 1, the slope of 8, and the constant of variation, k equals 8, that is, the slope tells you the rate of speed traveled, because it's d equals rt, and so that value, that's the rate, that's the speed that they're moving. What speed are we talking about here? 8, we need what kind of units? Well, look at how do you find slope? You take the y values over the x values, so it's the y units over the x units, miles per hour, 8 miles per hour. So we're going to be doing something similar with your roller coaster tracks when it comes to analyzing the safety and the thrills.